So in the last video, I got as far as talking about the hybrid filter I made by essentially joining together the start of a cascade filter with the rest of a ladder filter, and then using the start of the cascade as a way to implement resonance with slightly more control. I also talked about how, whilst this worked almost exactly how I wanted it to, it still felt like I could learn a lot more from it based off of how I'd basically just placed two different filters together, and I hadn't really fully looked in depth at how I could improve the circuit and really make it sort of my own. And this video is going to cover what I looked at over 2 weeks for this, because they go very closely hand in hand, and it seemed odd to cut research halfway down the middle and then immediately pick it up again in the next week. So this video is going to be posted on both the weeks that it applies to. And the way I first thought to try and improve my circuit or modify it further was to change what I was using for the ladder. So rather than using diodes or transistors, which is what Moog use, I thought about using vacuum tubes. Now, vacuum tubes are basically an outdated version of transistors or diodes. And the way that they work is they have a glass housing which has a vacuum in it, where the name vacuum tube comes from. It then has, for the most, or usually, an isolated heater. It then has a cathode and an anode, which is usually referred to the plate as the plate. So we have the heater, the cathode, and the plate. Now, this would be a basic diode vacuum tube, and unlike a regular solid-state diode, which has an activation voltage of 0.7 volts, vacuum tubes need to run at much higher temperature, or much higher voltages, sorry. So generally, whilst it can be run at lower voltages, it's recommended that a vacuum tube like this is run at a minimum of 12 volts, because they are designed to be able to handle hundreds of volts and even kilovolts if necessary. And this ended up coming back to bite me in the future, because more of just a little mind blank I had is, in the last video I mentioned how diodes, when you connect them in series, you add up their activation voltage. So that would be, instead of the 0.7 volts, 1.4 volts for the full activation voltage here. And vacuum tubes work the exact same way. So instead of two being run in series, you get 24 volts rather than 12 volts. And that came to be an issue because with my power supply, I wanted to be able to run it with plus 12 volts, ground, and minus 12 volts, which means my maximum potential difference was only 24 volts. So if I was to chain more than two vacuum tubes together, then I physically wouldn't be able to power it at the recommended minimum voltage. Again, though, you would have to create the bias voltage, so you can use something very similar to what I showed with, or what I talked about with Moritz Klein's diode filter, where you have two op amps adding in a voltage that which is used to spread out the signal, like so. So that would be your original input signal, your positive and your negative bias. Now, with vacuum tubes, though, there are many different types. So the one I talked about here, this is a diode vacuum tube. The other, and arguably more common version of a vacuum tube, is called a triode. So again, it has the heater and the cathode and the anode all housed within a vacuum. But it then has something called the grid. And what the grid does is you apply a negative voltage to it, and it prevents electron flow between the anode and the cathode. Because whilst current in a vacuum tube flows that way, going from the anode to the cathode, that is conventional current, because there are two different types of current. There's conventional and real or actual current, which, whilst they work in exactly the same way, they are the same thing in essence. The direction in which they travel is reversed. So conventional current is what you tend to look at when you're thinking of a circuit. However, if you were to actually analyze it, the electrons would be flowing in the opposite way to what is mentioned. So what's happening here is whilst your current is flowing this way, going from positive to negative, electrons are being thrown out from the cathode above the heater. And I can't remember the exact name for the or the exact terminology for what this is called, but that was the basics of all vacuum tubes, that heating up a piece of wire containing electrons would cause them to be spit out, in essence, and travel up to what would be your positively charged plate. So the grid, by giving it a negative voltage, though, because you have negative electrons trying to flow through here, they repel each other. So your negative electrons coming up here get held down by the grid when it is charged negatively, which stops the current flow between the anode and the cathode. And it's not sudden, and like the diode, it's not sudden just it is or isn't allowing current to flow. It's a gradual curve. So you can adjust the amount of voltage on the grid to give a different effective resistance. So and how I thought to use that in my circuit is, instead of having it so that you're adjusting the upper and lower bounds of the bias voltage, you instead have a fixed bias voltage, and then you are changing what the voltage on the grid is, and you're using that to change the resistance for your filter. And I have drawn here, actually, the basics of what I thought that ladder filter would look like, or just the specific ladder. So that was an isolated part from the rest of the circuit. However, one thing I had to consider, though, was what specific type of vacuum tube I'm using here. Because triodes are the most common, but they do have their issues. And I have videos linked which will be able to explain it in much more depth than I do. But with a triode, you can get oscillations of current between the two of them, and that's all between the plate and the cathode. And that is due to how the electrons move, because when you start to apply that negative voltage, there can be a little bit of a pause or time where then the electrons need to start moving again. So to try and get around that, the tetrode was created. So it is almost the same as a triode. You've got your cathode and your heater, then you have your grid, and then you have your plate. And that's all in the housing. But then you have a screen grid, which is a secondary grid. So this is your control grid. Then you have your screen grid. And what you do with the screen grid is you tie it up to the plate with a low value resistor, typically of about 100 ohms. And what that does is it means that this is then charged as positive. So your electrons that would be slowed down by the control grid, once they've got past the control grid, they're then accelerated by the screen grid, as that has a positive charge, moving them to the plate faster and helping remove some of those oscillations. But again, the tetrode did come with faults as well. And that was more down to how the electrons were now moving a lot faster. And because of that, what would happen was electrons would reach the plate and they'd be traveling so fast that when they hit the plate, they could then knock out other electrons, which would then have to then come back around again, causing more oscillations, but at a more reduced level than the original triode. And that's where the pentode comes into it. And the pentode was not the final version of this line of vacuum tubes, but it's the one, or it's one that is more common today, whilst not being too, or it's more common today as it gives slightly more control. But the pentode, again, is very similar to the tetrode and the triode, as you have your heater and your cathode and your control grid. Then you have a screen grid and your plate. But then you have a third grid, which is a suppressor grid. So you have control, screen, and then suppressor grid. And your control is obviously already tied negative. Your screen is tied positive, but then your suppressor is tied negative again. And typically it is connected round to the cathode, like so. So you would then have your low value resistor going up to your anode, like that. And the way that this works is then your electrons that are sped up by the screen are slowed slightly by the suppressor, so that reduces their speed, so they're less likely to knock out any more electrons. But then any electrons that are knocked out, because they are also negatively charged and the suppressor is tied to the negative charge of the cathode, they get repelled a lot fast or a lot sooner, allowing them to return to the plate and then continue carrying current. So how I thought about connecting a pentode up would be, as you just saw there, I'd have the heater. So I'd have a positive voltage for the control there. I'd have the cathode, which would eventually head to ground, or the negative bias, I'll put it as. I then had my control grid, which would carry the control voltage, or CV, if you remember from previous videos. I'd then have the suppressor grid, the screen grid going up to the plate through a small resistor. And then I had my suppressor grid tied back to the negative bias or cathode, like so. And that would all be contained within the housing of the vacuum tube, like that. Which it then, though, gave me two possible options. I could either use the pentode, or I could use the triode. And the main differences in terms of audio applications is, it's very sort of nitpicky. So the pentode gives more physical control. It gives a smoother graph of control and a voltage over time. But then a lot of people like triodes because they seem slightly more expressive and natural, and that's because they add natural distortions to the signal, which a lot of people find quite pleasant to listen to. And that is why they're so common in things like guitar amps, even though they are a massively outdated technology. So I then had a look at more specific types of pentode and triode to see if I could find something that would be more suited to my needs. And I wanted it to be as low cost as possible, and that ended up being the decider, because the two vacuum tubes I looked at were the 12AX7, which is a double triode vacuum tube. So you have two completely isolated triodes inside a single vacuum tube, and I could find them for roughly £15 per tube. So I was getting two triodes for £15, or the EL42, which was a pentode. And the average cost of that vacuum tube was about £10 each. So that means if I was to use, say, 6 triodes or pentodes, I'd only need to buy 3 of the 12AX7s, so that would be about £45, whereas with the pentodes, that would be about £60. So I chose to go for double triodes, more from a cost perspective, and did also consider looking for alternatives, and you will find out I'll explain whether I found any further on. But I believe I did decide just to stick with the 12AX7s, as they are commonly still produced and used in guitar amplifiers, which meant that if there was ever a fault with them, I could very easily find replacements. But in the next video, I'll talk about actually designing the vacuum tube filter and where it inevitably went wrong, which you will see later on down the line.